Okay, so in this video, what we want to take a look at is how do you multiply and divide within this new system called complex polar or trigonometric form. It may seem a little strange. There's some places where you might look at it and go like, why in the world would you do such a strange, complicated, honestly, sometimes you look at it as like, wow, why would I do a problem that takes 10 minutes when I could have done it before in 2? There's a reason why which will become more clear in later videos, but I'm just kind of developing a process for right now. So we're going to take a look at what we have done in the past on how do you multiply complex numbers and divide them. And so let's take a look at that over here. So I just had a couple of questions to look at. So keep in mind, this is a complex number multiplied by another complex number. And so what you have been trained to do is distributive properties. Minus 5i, and of course, one of the cool things about complex numbers is they're called a closed set, meaning if you add two complex numbers, you get another complex number. If you multiply them, you get a complex number. And if you divide them, you get a complex number. And so remember, negative I squared is actually positive 1. We got 11 and minus 3i. So notice the product of two complex numbers is itself a complex number. Or if let's just say we picked one that was a little bit more obnoxious, you're going to see why in a little bit later. Let's say we took 2 root of 3 plus 2i. You're going to notice that I'm playing with something that is going to lead us towards the unit circle. And 5 minus 5 root of 3i. So I've got these two different numbers that have a little bit of a play of special right triangles there and a little bit of unit circle. And let's go ahead and multiply those two things out. So the first thing we would have would be 10 root 3. Then out here we would have 2 times 5 is 10. Root 3 times root 3 is 3. So 10 times 3 is 30. So we get negative 30i. Going over to here, I have a plus 10i, and last here I've got a negative 10 root 3i squared. Now, of course, I squared being negative 1 makes us a positive 10 root 3. So all told, we get 20 root 3 minus 20i. And not by accident, you're going to notice that something that was very unit circle, something else that was very unit circle, things that have to do with special right triangles, and I got another one that has to do with special right triangles. Similarly, back in the day, when you looked at a problem like, let's say, negative 6 root 3 minus 6i, I'm not going to only do things that are unit circle or special right triangles, but for the moment, that's what I wanted to look at with you. And so imagine we had these two complex numbers and we wanted to divide them. Now, the trick that you learned back in the day, I set my pen somewhere else. There it is. What you learn is to multiply by the complex conjugate of the denominator. Now, you can see that's kind of weird, isn't it? Because in order to actually divide, I have to now do what we did right here now twice, and then get a result, and then go a little bit further with that. Now, the reason we did this complex conjugate thing is when you look at the denominator, your first piece, notice this outer and inner piece end up disappearing because I got a negative root 3i and a positive root 3i, which cancel. And then root 3i and a negative root 3i would make minus 3i squared, which gives us a denominator of 4. Now, the numerator, well, not quite so nice. 3. I've got a positive I. I've got a minus 6i. And last right here, I've got positive root of 3i squared. And if we did a little bit of cleanup, positive 6 root 3i squared, do a little bit of cleanup, we ended up with a total of negative 12 root between this and this, because that's a negative. And I got a plus 12i, and I can go ahead and reduce that ever so slightly. Both of these are divisible by kind of a curious result here that we something that is a special right triangle divided by something else that's a special right triangle, and we got something that's a special right triangle. Now, moving on a little bit, I'm going to go ahead and digress a little bit and imagine that instead of looking at it in this a plus bi or rectangular form, what if we were dealing with numbers that were in this polar form? So this is going to look very, very different, and this is really a proof of something that you're going to see. And at first, it's going to look like a really long way to do this problem, but it's going to be a really good reason why. So imagine that C1 is R1 cosine theta 1 plus I sine theta 1, and Z2 is R2 cosine theta 2 plus I sine theta 2. Now notice that is that trigonometric form that I mentioned in the previous video. And we want to multiply these two things together. What would happen if we do? Well, it's not gross, but we're going to kind of take our step through it. So that would be R1, R2. I would have cosine theta 1 plus I sine theta 1 times cosine theta 2 plus I sine theta 2. Now that looks pretty bad, and it's kind of worse because now I have to distribute this just like I did in these problems up here. R1 and R2 weren't that hard to deal with, and so let's see what happens. And one thing I am going to do is you notice when you start multiplying this out, some of them are going to be real and some portions are going to be imaginary. So I'm going to choose to try to rearrange it as I go just a little bit so that it actually saves us some time. So notice this first product, cosine theta 1, cosine theta 2 is real. Also, this portion right here would also be real because if I multiply I sine times I sine, that would be I squared, which is negative 1, sine theta 1, sine theta 2. I'm going to put a parentheses around that because the product of these two pieces right here and right here were real. As it turns out, when I go in and I do the other pieces, this outer piece and this piece right here in the middle, those are going to be imaginary. So I'm going to put an I right here. And what happens when we do that multiplication, I have a sine theta 1, cosine theta 2, and then out here, I would have a cosine theta 1 and a sine theta 2. It's a C right there. Well, that looks pretty bad, but if you go back to the card or the trig identities that we learned back in the day, we actually have this sitting in our card before, because notice this is the cosine of alpha cosine beta minus sine alpha sine beta, which is the formula that we had for how you multiply, how you actually add numbers, cosine of alpha plus beta. Plus beta 2. And over here, sine theta 1 cosine theta 2 plus cosine, that's just the sum. And so that's the sine of theta 1 plus theta 2. And so as it turns out, if you want to multiply two numbers in complex form, all you have to do is multiply their radii and add their angles. That's actually not too bad. And so as a result of that directive, I had a couple of examples just to show you how we multiply if you are in this form. And then if you're not in that form, what can we do to get it in that form? Before I do, I'm not going to do this proof. It just takes a long time. But in a similar fashion, here, notice when we multiply, well, we divide. And over here, when you multiply, you add the angles. So when you divide, kind of makes sense. It is very important that you could use the cis notation here, and that these angles will always be the same. So, quick example here. Let's imagine we had a series of values, and a lot of people like to use the letter Z for these problems. Imagine that my first letter Z is 5 CIS 35 degrees. But Z2 was 10 CIS 50 degrees. And last, let's imagine Z3. Because we can just go crazy with it and have as many things as we want. 125 degrees. I actually got super lucky with this. I just made those three numbers up and something kind of cool happened in that. But if you were in this form, the product of Z1 5 times 10 is 50. CIS, to add those things, I got 85 degrees. Now, in reality, nobody actually likes this kind of form. They like A plus BI better. So what we usually will do is get it into this form early and then transition back to the other one. 85, 4.358. And if I take 50 times the sine of 85, 49. I'm done. That fast, just some quick calculator work. If we wanted to take, say, 1 divided by 3 in a similar fashion as we did before, let's just CIS. I take 35, I subtract 125, I just got 90 degrees. Wait a minute, that's a really nice unit circle. That's where I got lucky. Turns out the cosine of negative 90 is 0, which is kind of cool. And the sine of negative 90 is -1. And so that result, if you add the math on that, you just get negative 5/8, which is actually kind of cool. You could put 0 minus 5/8, but you don't really need to. Or if we said, hey, what about Z3 times Z3 times Z3? Can we do that? Can I take Z3 times Z? Well, I can. Because then that would just say, take the radii, 8 times 8 times 8. That'd be 512 CIS. And then I would just take 125 plus 125 plus 125, which is 375. By the way, here, that should tell you that both values should be positive, and it turns out 512 cosine would be 494.544, and 512 sine 375 is 0.515. Now, going back to what I mentioned to you earlier, let me show you something that's kind of cool. Earlier, I had you try this problem right here, and we multiplied this by this. Now, again, I know some of you guys would think this would be crazy to do it this way because the other way was hard, but not that bad. That's radius of 4 or a modulus of 4. It creates a special right triangle to the right roots of 3 and up to I. This one similarly has a radius of 10. And when you go to the right 5 and down 5 pi over 3. But now that if I've turned it into trigonometric form, this product formula that we just had tells me that I will get 20 and 2 pi, pi over 6 plus 10 pi over 6 would be 11 pi over 6. Now this is a good answer. That answer is a valid answer. It's done right now, but sometimes we like to go back to that other form. That other form, this turns out the cosine of 11 pi over 6 would be 3 over 2, and the sine of 11 pi over 6 is negative 1/2. If you went back and looked at what we did earlier, that's exactly the same answer we got before. And in a similar stroke of luck, when we take a look at the one where we did the division, negative 6 root 3 minus I, and we divided it by 1 plus I root 3, we could turn this one into 12 CIS 7 pi over 6, and we could turn this into 2 CIS pi over 3, Again, it does take a little legwork to convert into trigonometric form, but now that we're there, 12 divided by 2, of course, is 6. This is, let's divide these. 7 pi over 6 minus 2 pi over 6 is 5 pi over 6. Again, valid result. Usually, it's frowned on to leave it in that form, so we go ahead and is negative root 3. And the sine of 5 is I. And so my final answer is exactly the result we got last time, which is kind of cool and kind of weird. And in the next little set of videos, we're going to talk about what happens when you deal a little bit more with exponents. I hope that actually worked. I'll have a couple of practice problems with an answer key for you to look at to see how that works for you. Hey, it's been a pleasure. See ya. Bye-bye.